we'll get right started back in with this section where we're going to start talking about the LISST-AOBS instrument and the theory behind how that combination works. As we saw from one of those last slides that Ola presented, the ABS didn't match the physical samples very well closer to the riverbank. The rationale there is because the current is slower, so there's less suspended sediment load and a lot more of the smaller particle wash load. So that wash load is seen by the turbidity sensors that are highly sensitive to smaller particles, but not very well by the ABS, which sees mostly the larger suspended load. So to address that issue, we started down the rabbit hole of how to improve that relationship. So what if we could combine the output of the ABS and a turbidity probe? Recall this plot, similar to what we looked at earlier in the presentation, that showed the response per mass concentration for both the turbidity in blue and the ABS in green as a function of particle size. So if we look at that blue turbidity curve, we again see that it has a strong response compared to the ABS for fine particles. The ABS, on the other hand, has a much stronger response for the larger suspended load particles. Furthermore, that response is relatively flat for even larger particles, which means that there is little dependence of the ABS output on particle size for those larger particles. Again, the acoustic signal is less sensitive to particles smaller than 60 micron, and that's why that near bank profile in the Missouri River data showed underestimates by the LISST-ABS. Is there a way to combine these two scattering signals from these two physically different sensors into a combined estimate, something that would be similar to the red curve that's shown here? If that's possible, then we'd have a sensor that would have minimal sensitivity to grain size, at least up to around 400 or 500 microns or so, where the ABS starts to fall off. And that would respond mostly to suspended sediment concentration, not grain size. It turns out that this is possible. Sequoia has actually got a patent pending application for a method that combines the signals for the two sensors in such a way that that combined response, the red line, has minimum variance. In other words, that it is as horizontal as possible. We're not going to go deep in the mathematics here. Yogi's published that in a paper elsewhere. Suffice it to say that we take advantage of the fact that the two curves cross each other at one point at some particular particle size. It can be shown that the signal from the two sensors at this exact point can be used to minimize the variance of the combined response. You can then simply apply a pairing factor that we call gamma to the output from the turbidity sensor and then add the ABS output to it. The result is the AOBS output in milligrams per liter, which is the red line on that figure. So it's possible to match any turbidity sensor to an ABS in order to create your own AOBS. You just need a set of pairing particles that we actually can provide and a license to pair them that we also can provide. This is a patent pending method, so that is a requirement. Then you find the ratio of the ABS output to the turbidity output, where you're measuring with both sensors at the same time. This gives you gamma. The combined output, the LISST-AOBS output, is then ABS plus gamma multiplied by the turbidity. So it's very important to mention that for this pairing, it's completely irrelevant if the turbidity sensor is calibrated in NTU or millivolts or volts, whatever. The turbidity sensor units don't matter. The actual concentration of the particles during pairing is also irrelevant. It just has to be enough so that you get good signal for both sensors. Really important, the pairing is not a calibration or any form of multivariate regression. That's a misunderstanding of how this method works. If you think of it that way, the entire idea behind the AOBS is that the variance of the combined response between the two sensors is minimized via that factor gamma. It's also important to realize that the location of the crossover point between the two sensors could vary a bit. The green curve showing the scattering intensity for ABS is fixed because we only have an 8 megahertz ABS, but the blue curve for the turbidity sensor could move up and down depending on the wavelength used. For practical applications, this isn't really going to change things more than a few percent, But if you're going for the highest possible accuracy in the pairing, you would compute that curve for the specific turbidity sensor wavelength and use a pairing factor based on that modified curve.
So that's the very brief theory behind the AOBS. And if that needs to be explained in a lot more detail, we can certainly take that during the Q&A. I saw a note in the comment that some people requested the paper to be published. And I realized we forgot to actually put the reference in right here, but we'll take care of that later on so that everybody has a chance to read that. The design of the AOBS, well, it's really mechanically, it's fairly simple. It's a LISST-ABS, any turbidity sensor and respective cabling and some pairing, and then you can create your own. Now, we also at Sequoia, we provide fully paired and ready to go AOBS as well. For that, we have decided to just go with one turbidity sensor in order not to have to integrate turbidity sensors from every single manufacturer. We use Turner Designs Turbidity Plus sensor. Turner Designs is in California. I've made turbidity sensors for decades. And then we have a Y cable between the turbidity sensor and the ABS that contains sensor ID, and it also contains the pairing info for the sensor. So we actually have a little bit of electronics inside that Y cable, so that if you have the correct data logger, then it can read the pairing info. We'll get to that in a second. And because we have all that available as a package with a Nexsens X2 logger from Fundriest, who we've talked about before. And we are not going at Sequoia, we are not going to provide any other turnkey options, because then we would have to handle turbidity sensors, as I said, from every single manufacturer. How does the AOBS actually differ when we compare to the ABS and turbidity sensors? And the AOBS really does provide the response of the red curve. So we have minimized the variance from grain size variations in the output, and it responds mostly to changes in concentration and not to changes in particle size. So you can see, comparing the red curve and the green ABS curve and the blue optics curve, that is clearly a better response. So it's simply a lot less dependent on variation in grain size than either the ABS or turbidity on their own. There are some differences when we talk about power and connections and output from the AOBS. First of all, the ABS had SDI12, RS232 and analog. The AOBS only has SDI12 output. It's the same connector that's on there. So all the cabling that you might have from an ABS, in terms of connecting it to a data logger, that would still work. You can take the existing cabling and that you have for an ABS and just plug in an AOBS, and then using the SDI12 pigtail that we talked about a little bit earlier, and then that would just work. It takes a little bit more power when it's sampling, because it has to drive both sensors. There's also a wiper on the turbidity sensor to minimize fouling. That's, of course, for long-term deployments. We do want a wiper on there to make sure that the optics stays clean and we get a good turbidity signal. Because, of course, if you don't, then everything falls apart. Then there's the Y cable that I mentioned, which acts as the adapter for the turbidity sensor. And it has a little circuitry inside where we store the pairing information from the pairing exercise that we do before we ship it out. The sensors do appear as two separate sensors with separate addresses. That's important when you're using it for SDI12. You have to address each sensor separately. So you get the signal from the ABS, then you get the signal from the OBS, turbidity sensor. And that's really what this slide is showing, how the output should be handled when you're programming up your logger for that. And we suggest that you first run the wiper to make sure that everything is clean. Then you get a 30-second average. And we'll talk about this 30-second business later on as well, because the sampling volume is relatively small in the ABS and for the turbidity sensor for that matter. So in order not to have too much variability in the data that are just purely related to turbulence, then we recommend averaging for 30 seconds. After 30 seconds, you retrieve the ABS and then the OBS as separate values. For the AOBS, as it comes from Sequoia, then we just provide the turbidity sensor output in raw voltage and the output in concentration. And then the user has to calculate the AOBS value in post-processing by using the pairing factor, which is stored on the instrument. Except if you use the Nexsens X2 data logger together with the AOBS. We've worked with Fundriest, so the data logger from Fundriest the X2 and X2 STL loggers, they support plug and play with the LISST-AOBS. So it will auto-detect the LISST-AOBS and read the pairing information from the Y cable. And then it will log the ABS data in milligrams per liter and the turbidity sensor in volts. And it will then calculate the AOBS concentration based on the pairing information it reads from the Y cable by applying that gamma factor that Wayne has introduced to the turbidity sensor, and then add the ABS concentration. There's options for that too, to communicate the data to Nexsens server via either cellular, radio, or Wi-Fi. So it's a very versatile data logger that they have for that purpose. And it exists both in a submersible and a non-submersible version. And both of them support the plug and play with the AOBS. So how well does it actually work? So here's there's a lot of data on, especially on the left plot here. So let's see if we can keep track of that. You can see there's a number of curves on the left plot. Some are with pluses, they are turbidity data. Some are with marked with circles, and they are ABS data. And then there's all the data are from samples or particles with various size ranges. You can see there's some 4 to 8, 5 to 10, 10 to 20, and so on, particle sizes. There's also some called ABS A2, A3, and A4. And those are some other standard particle sizes that we use. But you can see we have particle sizes from essentially 4 to 150 microns. And then we have measured with the turbidity sensor and the ABS, we have measured the actual concentration over a series of concentration ranges. For the turbidity sensor, which is the lower half of the data, that's all the curves that has a little plus in them. You can see, for example, if you look at a concentration of 100 milligrams per liters, you can see that we have an order of magnitude or more of variation in the output from the turbidity signal as expected from what we've seen before. We see the same for the ABS, and that is because that's also as expected, because you can see the curves that, for example, for 100 milligrams per liters, the ABS starts to show actually 100 milligrams per liters. Once we get up to particles that are 40, 50 microns and larger, then all the curves start to fall on top of each other. For particle sizes that are smaller than that, then the signal from the AOBS is also smaller, so it underestimates as it should. But when we combine the two, that's the plot on the right, where we then have used the pairing factor, and we then plot the actual concentration on the x-axis versus the AOBS concentration on the y-axis, and the blue line is the one-to-one line. Then all the data falls around that within a factor of 2. And it's really important that you realize what you're looking at here is not a calibration curve. There has been no calibration here between the AOBS and the actual data. This is purely from the pairing the AOBS with the turbidity sensor, where we are pairing the output in voltage and combining it with the output from the ABS to get the actual concentration in what we call the AOBS Super-Turbidity signal. It's really important to realize, and I can't emphasize this enough, this is not a calibration you're looking at on the plot to the right. It is simply the output from the AOBS as it comes, plotted against the actual concentration. And all the circles and the pluses, they denote various sizes. So you can see, regardless of the size, we have the blue circles, for example, that's 4 to 8 microns, and the AOBS estimates that almost bang on. And we have the red pluses is 125 to 150 micron particles, and we also estimate that very well with the AOBS. So it really works surprisingly well. Well, actually, it works according to theory, as Wayne has presented. We can also look at the plot here that we've seen before from Bundgaard et al. And this paper is listed in the references which we have at the end of this presentation, so you can see that too. And to some extent, this is the same plot. This is just how a turbidity sensor responds to all the variations in particle size and concentration. We've shown this initially early on. Wayne presented this very clearly, but it's just to contrast what happens when you look at just turbidity data versus the AOBS data. We can also look at some laboratory samples we've taken. So here we have on this plot, on the top plot, we show the signal from the ABS in blue, and we show the voltage signal from the OBS in orange. And we had the AOBS working in a beaker with a mixer. And then we introduced about 1200 milligrams per liters of 5 to 10 micron particles, and about 1200 milligrams per liters of 75 to 90 micron particles. Then we made sure that was well mixed. And you can see that's what's going on the top plot from sample 0 to around sample 30. And then we stopped the mixer. And when we stop a mixer and you have 75 to 90 micron particles in a beaker, then they drop like a rock. And you can see that in the acoustic signal, it drops to 0. You can see the optic signal doesn't really change a whole lot. It stays fairly constant. There's a little bit less variability. We don't have the variability from the large particles, but it's essentially the same. There's not much change in the optics. So the optics didn't see the large particles. It didn't see the 1,200 milligrams per liter. The bottom plot shows the combined response, the AOBS response. And you can see that we start out with a concentration of about 2,500 milligrams per liters, which was what we actually put in. We had about 1,200 of 5 to 10 micron and 1,200 milligrams per liters of 75 to 90 micron particles. And you can see when we turn off the mixer and all the 75 to 90 micron particles settle out, then we are left with about 1,200 milligrams per liters in suspension, the fine particles. And when we turn on the mixer again, everything comes back up to where it was. And we have a little paper on our website that describes this as well and shows this figure in more detail. So here it's really important also to realize that you see we have the OBS or the turbidity sensor signal in volt. We have the ABS signal in milligrams per liter. When we combine them using our pairing method, then we get the AOBS signal in milligrams per liters. No correlation between the optics and the acoustics. It's a pairing, as Wayne has explained. How well does it work? We remember where the LISST-ABS was in this plot, down in the bottom left with high accuracy and low precision. The AOBS certainly starts out here, and then we would argue that it moves a little bit in this direction towards higher accuracy and high precision sensor than the ABS does. So the key takeaway points regarding the AOBS is that implementing this pairing factor, where we combine the turbidity and the 8 megahertz acoustics, then we get a really, really flat response, as flat as it can get, as physics allows, over a size range from very fine particles of about 1 micron and up to about 500 micrometer particles. And there we take advantage of the fact that they have opposite tendencies in that Ka less than 1 regime, where the turbidity sensor compensates for the lack of the ABS in that regime. And in the Ka 1 and larger, then the ABS takes over and supplies the signal. And that's the principles that essentially make up the AOBS.